Hello everyone! Sorry, I couldn't present this webinar today, so I made the recording last Sunday. Today I would like to share some lessons with you from managing bridges in marine environment. Most of these lessons are learned in New Zealand, this is applicable to Australia as well. And before we begin with the lesson 1, I would like to say that asset management for me is an art of getting the best out of limited resources available. We all know that resources and budgets are never there. And low-cost solutions can actually offer great value, but we need to understand the risks that comes with it and make sure we address them and understand them. So, lesson 1. Marine structures rarely last 100 years. Unfortunately, they not even last 50 years in most cases. They technically do last, but they not perform, like the structure on this picture. Unless timely maintained, of course. Almost all non-encased piles which I inspected had deterioration at just 25 to 50 years. And why is that? Because at that time, shorter design life was the norm. Structures were often designed for 50 years, some of them even shorter. People at that time anticipated that the structures would be replaced with bigger bridges, bigger wharves, and would be essentially obsolete. No one would need them. But this didn't happen for some reason. Construction was easier and faster, less safe of course. Design codes consequently did not require it. They did not ask for 100 years, like take Australian HB77 for example. And another aspect is chloride-induced corrosion was understood, but it didn't actually made its way to the courts yet at that time, following significant advancement in mixed designs. Now let's talk about cracks. I would like to focus on a particular type of crack induced by corrosion. And when you see these cracks, it's a late warning. So by the time you see these cracks, the corrosion is going on, and you're likely to see section loss at 30 to 100%, with quite often a lot of stirrups being completely gone. And it's even worse for pretension reinforcement, because once we get the strength failed, it leads to a distribution of forces in the entire element, which could lead to various consequences. I would like to simplify here a bit, but without cracks we're dealing with a long-term corrosion, because it's driven by chloride ingress and corrosion takes off very slowly. But as soon as we have a crack, oxygen gets in and we're dealing with oxygen-rich environment, which accelerates corrosion by many times. And unfortunately, these cracks are very easy to miss, because they're often hiding behind marine growth, mud, or could be simply on non-visible faces. As often happened to me, you would inspect the element or a structure from the shore and it all seems alright, but as soon as you get on a boat, get around, you see these cracks. So pay attention and make sure that you inspected the structure all over. And bear in mind that sometimes you actually won't see the staining. There are only 2 reasons not to repair these cracks. Is if you're not expecting this asset to last any longer, and if you're 100% sure that the structure has a lot of spare capacity. And that leads us to the next lesson. Clean well, inspect thoroughly. So start with the tidal zone. Focus on piles, pile caps and other elements exposed to marine growth. Without proper cleaning, it's very easy to miss, I'd say, about 70% of the cracks and deterioration going on and other damage. How to clean? I would recommend high pressure water washing or even air power tools. Both of these methods work well underwater, and you do need to clean underwater sometimes, not very deep, but I'm talking about 200, 300, sometimes 400 millimeter deep to look at your pile a bit closer. Corrosion can extend underwater, especially in a tidal environment. If your element embedded in mud, it's also worth excavating the top layer and make sure to inspect it. Corrosion may hide there, but this layer still provides a lot of oxygen. If you consider that you have no condition, no deterioration going on, when you still should look further and inspect it. If your structure is already 25-30 years old, there is a good chance something is going on. So that's the first factor. If you're dealing with tiny piles or pretension reinforcement, then it's also another good reason to look at it. If you don't have any record, assume worst. When you suspect low cover, I would typically look at the workmanship of the entire structure, and if you suspect poor workmanship, that's a good sign that there might be some spots with a very low cover, especially near the water. If you're dealing with steel casings, clean them as well and check for integrity. If it's a structural casing, if you don't know, assume it is structural or consult with the engineers. I suggest you to verify wall thickness and understand the corrosion rate and whether this casing still provides adequate performance to the entire structure. If you found some holes in casing, you could actually take advantage of it and test your concrete through these holes. Afterwards, holes could be patched by applying coating, by tape, or in welding a steel patch over it. And now we'll get to my favorite lesson. Actual cover on the structures is typically less than what you see in the drawings. We all know that. That's why today we have post-pour cover checking. So risk of corrosion in these low cover spots will be much higher, especially if we're talking about marine. It's essential to find the spots early and do something about it. There are two main tools to measure cover. One is a cover meter. It's very accurate, it's very easy to use. At the same time, it's very time consuming, except some later models which allow you rapid scanning across large faces. And it offers a limited depth. GPR on the other side, more expensive, but it provides you much better insights about what's going on, and it's not just measuring the cover. It actually gives you a full picture of reinforcement in the upper layers. It does require calibration, but it works on the larger spaces and collects a lot of data within a short period of time. Then ask yourself, are the spots still at risk? If they are in marine, in the tidal zone, then probably yes. So you do need to consider local protection, like jacketing, coating, preventative repairs. Because if you just decide to delay or monitor it, keep in mind that it's like investments. Those risks keep compounding. And make sure that you keep your records organized, because these documents would matter for someone who will come after you. Those cover readings are very helpful on the next stage, because they provide essential information for residual life assessment. But that's only one of many parameters. Lesson 5. What if our concrete have good cover, but it doesn't contain any ACMs like fly ash and GGBC microsilica? Chlorides could still penetrate this concrete very easily. I did see a number of structures which provided a good cover. However, chlorides getting in with no problem in fairly short time, I would say about 30-40 years. So search for the records of the mix. It's typically written on the drawings. If you don't have drawings, just assuming that because the structure in marine environment is built of marine concrete, could be quite dangerous. I'd say the easy way to test your concrete is with resistivity testing. It's fairly inexpensive and very helpful test to confirm your assumptions. The next step is understanding how chlorides penetrated, how deep chlorides penetrated into your surface. Yes, it does require taking some course and professional subcontractor who understand what they're doing, as well as lab testing, but it provides you essential information about how your structure is behaving, especially if you're looking into 20, 30, 40 years old structure. It does give you a real understanding about how quickly chlorides getting in, and it's extremely helpful for residual life assessment. And where you should focus your testing? Of course, start with the tidal zone and test bottom up. If the tidal zone is healthy, other zones will be healthy too, but be aware other zones might have lower cover sometimes. And pay attention to the areas where salts could accumulate. It does require some experience to understand and see these zones. As a rule of thumb, look at the zones which are not getting rain washed. I'll tell you an interesting story here, which is my next lesson about a bridge, which I inspected a few times and other engineers inspected it. It only showed minor spalling on deck cantilevers. Hammer tapping did not reveal anything significant, at least, but a few years later we had to replace the entire deck. So what happened is this deck, because of corrosion, have cracked horizontally all along its plane, allowing corrosion product to expand into this crack without being noticed and without producing typical spalling. Very interesting case, I should say. By the time we discovered it, the corrosion progressed so far that we saw complete section loss on some main reinforcement. And that brings us to a question why corrosion assessment matters. Because with non-destructive tools, things like that could be detected quite easily. I'm talking about electric potential mapping or half-cell potential, which could easily detect those risky areas. It's important to say, though, that it does detect a risk of active corrosion. It does not confirm corrosion. And it's often used with a resistivity testing, which I mentioned earlier, which also helps to assess the rate of corrosion. This test is non-destructive and very cost-effective. Some of the modifications of this equipment actually allow to scan very large areas fairly quickly. Although you do need to drill a little holes to connect to the reinforcement, but these holes could be repaired quickly. It's quite sensitive to chloride-induced corrosion, which is what we need. And as an output, you will be given a risk map which shows all those hotspots where you should search for corrosion. And it does typically follow that with an isolated breakout to confirm whether corrosion is there or not. Lesson 7. I'll tell you two stories here. One about deteriorated pile extension. Once we were building a new bridge next to the existing structure. So at the time of the piling, the contractor reported significant crack in the older abutment of existing structure. What happened is 1/3 of the abutment, as soon as the piling commenced, cracked and started tilting a bit. Everyone suspected, oh, probably engineer did something wrong, and they didn't take into account the existing supports. But in fact, once we dug down, we found there's no pile underneath this section, which was very strange. We did find a pile about 1 meter deep. So, and what appeared to happen, quite often the piles could be driven slightly deeper than you expect. And the contractor at that time seemed to extend this pile with the side concrete, which wasn't as durable. So this concrete almost completely deteriorated, leaving no support and no steel and no connection to the abutment, causing this part obviously to move as soon as we given it space to move. The other story is about piles which were driven upside down. That might also happen. We were dealing with a bridge which was actually built in 2 stages. Stage 1 involved 1 lane, and it's 3-span bridge as far as I remember. The other lane was built 1 year later. So, and what we found, because we were dealing with some corrosion issues in the tidal zone, that 3 piles on one of the piers of the second lane did look quite unusual. So once the contractor started breaking in, we quickly realized that there are no steel at all compared to the drawings available for this structure. Then we looked into other piles which exhibited some corrosion, and we did find completely different picture. The only reason why this could happen, as we later concluded, is because these piles were driven upside down, presenting a lot of structural issues, but we got this solved. So now, once you get out in the field, make sure you think about these cases. Then things like that could happen with you at any time. When you should start thinking about digging and exploring? When you suspect an evil settlement, you often would see tilting or cracking in the supports. When you see the pile tops looks different to the rest of the pile, I'm talking about different color, different texture, or even different shapes sometimes, I could tell you that this pile was extended on site. I would pay close attention to this. Especially when you're planning on building a new structure or extending the structure, any sort of new construction beside it, then existing structure should be looked under the microscope and make sure that it could survive the new construction. And it's not as difficult as you may think, because hydro excavation is a very safe and effective method today, and it's available anywhere. Now let's talk about pile encasement, which is my probably favorite topic. I taken this picture on a holiday around New Zealand, and what you see here is the jackets were built to protect the existing piles, but from what appears, especially you could see that closely on the picture on the left, the jackets didn't extend as long as you would expect them to, and it's clear to me that about 0.5 to 0.7 meters of the pile just above the low tide wasn't protected, and it does show significant deterioration and corrosion issues. On the other side, These are some of the jackets which are not perfect, but doing much better job. They do extend all the way, slightly below the low tide, and protect the most vulnerable section of the piles. Encasement could be very effective, but it's not simple. Designing it right could be quite complex. I'll talk about it on the next slide. One mistake could actually shorten the lifespan of the pile quite significantly. While well designed with sacrificial cathodic protection could give you another 20 plus years of the lifespan. The key thing here is to address the cause of corrosion. Key design consideration for pile encasement is understand your life extension, what you're trying to achieve. Also, think about whether you're restating capacity or not. If you have some significant section loss, you might need to do it, but talk with your structural engineer and make sure you analyze these piles, because not all the bars need to function. Once the pile is there, it mostly takes compression, but there could be many cases here. Think about, once the jacket is suspended or with a grout in it, how much it would weigh and how you could support this on site. Of course, it's a contractor problem, but the contractor will come back to you and ask what options you had in mind. And also, once you are pouring in that filler, would it displace water effectively? Remember, we are in a tidal zone, so the water will be there, and we need to think how to minimize water presence. Then this grout, in some cases, could be epoxy, but most of the time we're talking about cementitious material. How it could key to the pile surface? I wouldn't recommend relying simply on roughness of the concrete and provide sufficient keying to grip to the pile. The other aspect of design to consider is chloride diffusion, especially if you're dealing with additional steel reinforcing inside the jacket, because your existing pile concrete would contain some chlorides, and as soon as the repairs are done, these chlorides will diffuse back into the jacket, into cementitious material, and this might cause very early corrosion if you're not providing sufficient cover or not addressing it otherwise, like installing stainless steel inside the jackets. UV degradation, like in the example I shown you before, if you install FRP jackets and leaving them on, think about how quickly they will degrade under sunlight. So consider coating if you do use FRPs. Depth of installation, I talked about it quickly previously, but make sure that you specified how deep your jackets go. And I would think about lowest astronomical tide or mean low water spring tide, and consider challenges which are associated with it. Last but not least, once the design is done, actually halfway through the design, think about all the construction steps. Constructing those jackets are much more difficult than you imagine. And unfortunately, none of the off-the-shelf solutions that I see on the market, which claims, oh, it's quick and easy, actually, it's never quick and easy. And you do need to consult with contractors and with suppliers about particular steps, ask them hard questions. Right. Let's now talk about coatings in a tidal zone. And I would present a few cases here. On these pictures you'd see newly applied coating, probably about 3 meters high, and the same coating on the left 1 year after, still intact with some marine growth on it. When you're dealing with high chlorides, especially once you already tested, it not necessarily means that your structure is done and there's not much you could do about it. And it's not necessarily means expensive repairs, because your actual corrosion threshold could be higher than these levels. And you might still have some time, especially if you have no cracks or other vulnerabilities on the structure. Coating might give you that time to plan and budget for the next stage. Coating makes sense because it's slow chloride ingress, and it's much cheaper than any other options typically available for repair. It gives you that extra confidence and it buys you valuable time to plan for the next repair, as I say. But what's important is to consider all the risks associated with it and make sure you did the risk assessment. Couple of tips here. Fill all the blowholes before you apply coating, because these blowholes could be an entry points for your salt water. And come back a year after to inspect your coating. Make sure that it's intact and undamaged. You will be surprised even with good QA of your findings. At least I did on one project. Final lesson, concrete superpower, which is proper curing. Curing is everything for concrete, because curing reduces permeability of concrete, which in turn slows down chloride ingress, which in turn improves durability and longevity of the structure. Curing time is everything. Ideally, you should cure for at least 7 days. If you're dealing with pile casing, keep them on as long as possible. Ideally, leave them permanently if the design allows you to do so. Again, if you do have to remove them, try to wait for the 7 days before you do so. A couple of tips here, and I would like to get a picture I already showed you, which illustrates an element with a Hessian cloth on it. I would recommend to inspect those elements very well. What I did find in this particular case, that about 50% of the area of this element was dry, with the entire underside not being wet cured. Also, if you're dealing with precast elements which have to be delivered green on site, consider plastic wrapping. Plastic keeps moisture in and allowing your element to cure very well. And to illustrate this point, you could wrap in plastic almost everything, as you can see here an example of a few boards. So, final thoughts on these lessons. While inspection and data collection is a technician job, it takes experienced expert to bring valuable insight into that data, into an understanding of what's going on. Not to say to determine quantities and locations and appropriate tests to start with. I always say that inspection is only as valuable as the thinking behind it. Now it's time for questions. I can't answer your questions right now, but I would welcome any questions on my email address, which is e.volkov@bcrc.com.au. Thank you so much for watching.